Hi everybody, let's begin our discussion over the CBSE pattern question exercises for mathematical reasoning. The first question for 1 mark says that which of the following is a statement among these two? Now for a statement, you know that a sentence is declared to be a statement provided it holds a truth value. If it fails to hold the truth value, it is no more a statement. There should be no confusion or doubt regarding the truth value of that sentence. If I talk about 6 has 3 prime factors, you all know that all the factors of 6 are 1, 2, 3 and 6. Out of 1, 2, 3 and 6 factors of 6, which are or how many are the prime factors? 2 and 3, right? So for the first sentence I can say 2 and 3 are the only prime factors of 6. 2 and 3 are the only prime factors of 6, and here it is written 6 has 3 prime factors. So I will say therefore 6 has exactly 2 prime factors, isn't it? 6 has exactly 2 prime factors. Therefore 1, 6 has 3 prime factors is a false sentence. More important than being false, important for us is that it is holding a truth value of being false, and therefore it is a statement. Therefore 1 is false and therefore 1 is a statement. It is a false sentence, therefore it is a mathematically acceptable statement. And x square plus 5x plus 6 equals 0. If I talk about x square plus 5x plus 6 equals 0, I know I can write this as x square plus 2x plus 3x plus 6, which is going to give me x plus 2 plus 3 times x plus 2, which is going to give me x plus 2, x plus 3 as the factors, which is going to give me x equals minus 2, x equals minus 3. So I'll say if x is equals to minus 2 and minus 3, then x square plus 5x plus 6 equals 0 is true. But if x is not equal to minus 2 and x is not equal to minus 3, then the second statement is not true, it is false. So there is no fixed truth value which can be assigned to this sentence, and therefore for different values of x you are getting different truth values for this sentence. So there is no fixed truth value. Therefore I will say that 2 is not a statement. Is it clear? That's how you need to describe the reason and then declare the conclusion. It's not a statement. Talking about the next question, we have write each of the following statements in the form of if then. Okay. If then. Here if you see, your you get job implies that your credentials are good. If you take you get job as a statement P, your credentials are good as statement Q, the very first sentence is saying P implies Q. P implies Q can be written as P implies Q, which is another name for if P then Q, right? So how will you write this sentence adjoining if then? It will be if P then Q. If you get a job, if you get job, then your credentials, are good. That's how you can rewrite the sentence using the phrase if then implication. And if I talk about the second case, it is you can access the website only if you pay a subscription fee. So you can access the website, take it as statement R. You pay a subscription fee, take it as statement S. So the second sentence is basically saying R only if S. You know that R only if S is another way of writing R implies S, isn't it? If P then Q can be written as P only if Q, because Q in this case is a necessary condition for P, P is sufficient for Q. So R only if S means S is necessary for R, that means this is just trying to say if R then S or R implies S. So that is if R then S. So how will you rewrite this? If you can access the website, then you pay a subscription fee. So that is, if you can access the website, then you pay a subscription fee. Okay? That's how you actually rewrite these sentences using if-then phrase. Then you have write the negation of the following statements. So there are two statements given to you, you have to negate them. That means deny what they are trying to say, and hence the truth value will also be opposite. For all positive integers x, we have x plus 2 greater than 8. What is the negation of the phrase for all? Quantifier. For every positive integer x, we have x plus 2 is greater than 8. Negation of it would be, if I am saying this is my statement P, I am writing not P. For every positive integer x, we have x plus 2 is greater than 8. Its negation would be there exists. You can write this complete quantifier. There exists a positive integer x, such that x plus 2 is not greater than 8. There exists a positive integer x such that x plus 2 is not greater than 8. It is a denial of this particular statement, which is saying that for every positive integer x, x plus 2 is greater than 8. Or you can also say in other way, there exists a positive integer x such that x plus 2 is, if it is not greater than 8, that means it is less than equal to 8. So this or this happens to be the negation of this first statement. Second is, some students are 25 years or older. Some. What is the negation of some? None. Right? Even if there is one student which is 25 years or older, its negation would be none of the students are 25 years or older. So what is the negation? So if I am saying this is my statement Q, then not Q is none of the students are of 25 years or older. Or you can also say, just write it in a positive sense, every student is under 25 or below 25 years in age. Every student is under 25, or you can say none of the students are above 25 or older. Fine. So this is alternative fashions of writing the negation of the same statement. Then we have what? Write the contrapositive. So after negation we have contrapositive. You should know, if we have P implies Q as my statement, then contrapositive of it would be not Q implies not P. So if two lines are parallel, then they do not intersect in the same plane. If whatever is being written after if before then is my statement P, whatever is being written after then till the full stop is my statement Q. You have your first statement given to you as an if-then implication, if P then Q. Its contrapositive is what? Its contrapositive is if not Q, then not P. If you know P and Q, that means you know not Q and not P as well. So just write down this statement by correct interpretation of not Q and not P, simple statements. So not Q, lines do not intersect in the same plane. If lines intersect in the same plane, so if not Q is denial of Q, lines intersect in the same plane. Q said lines do not intersect in the same plane, so not Q will say lines will intersect in the same plane. If lines intersect in the same plane, then not P. then not P. What is P saying? Two lines are parallel, not P will say two lines are not parallel. So if two lines intersect in the same plane, then they are not parallel. Fine. So if this is P and this is Q, not P will be two lines are not parallel, not Q will be that the two lines are not intersecting, they are intersecting in the same plane. Q says they are not intersecting, so not Q will say they are intersecting. P says they are parallel, so not P will say they are not parallel. As easy as that, and this is your very contrapositive. Second is x is an even number implies that x is divisible by 4. Now the moment you are saying implies, it is again the same thing. If P then Q, you are able to see that if this is R, this is S, then R implies S is your statement given to you, and R implies S is just another way of writing if R then S. So your second statement actually is R implies S, that is nothing but if R then S. Same thing, just written in a different fashion. So its contrapositive again would be what? Exactly same thing. The moment you have if then implication, you can very easily write the contrapositive. It is if not S, then not R. S is what? X is divisible by 4. So not S will be if X is not divisible by 4. X being not divisible by 4. Then not R. R is X is an even number. So not R will be X is not an even number. Then X is not an even number you can write, or you can write it's an odd number. It's the same thing. Clear? That is how you actually write the contrapositive of an if-then implication. Next, let's see what we have as the fifth query. By giving a counter example, show that the following statement is not true. If you can remember, we have done this article called Invalidity of Statement, which actually we prove by the counter example approach. So basically this statement says that this equation x square minus 1 equals 0 does not have a root between 0 and 2. If I need to counter this statement, that means prove this is false, I need a particular root between 0 and 2 of this equation. This is saying there absolutely exists no root between 0 and 2 of this equation. That means there is no value of x between 0 and 2, which when you plug in this equation, it gets satisfied. How will I be falsifying this statement? When I will produce a value of x, which when I plug in here, this equation gets satisfied. Moreover, that value of x is lying between 0 and 2. That would mean that yes, there exists at least one value of x between 0 and 2, which is the root of this equation. That would be my counter example. That is going to falsify this statement and prove this is invalid or false. Here if you see, x square minus 1 equals 0 clearly implies x equals 1 is one of the roots. X equals 1 is a root of this equation. And 1 lies between 0 and 2, isn't it? 1 strictly lies between 0 and 2. Therefore, I have got a root of this equation x square minus 1 equals 0, which is lying between 0 and 2. So this statement is false, which is saying that this equation does not have even one root between 0 and 2. So therefore, P is false, or you can write it is invalid. Is it clear? And that's my counter example. X equals 1 is my counter example. Next we have, write the component statements of each of the following statements and also check whether they are true or not. Okay. So if a triangle is equilateral, then it is isosceles. Right now you can see this is an if-then implication. What are the component statements? A triangle is equilateral. This is the first component statement. The triangle is isosceles. Second component statement. So for the first, I can say that the component statements, are P and Q, that a triangle ABC is equilateral. here I can say that a triangle ABC is isosceles. These are the two component statement which have been combined together by the if-then phrase to get this compound statement, which is if-then implication. So these are the two component statements. Now, based upon the truth value of these component statements, I will be declaring the truth value or validity and invalidity of my given statement number 1, because we have to show whether these statements are valid or not, or true or not. I know if P then Q is valid when? I should be aware that if P then Q is trying to say that whenever P holds, Q should hold. If P is holding and Q is not able to hold in that situation, then if P then Q is an invalid statement. If P then Q clearly means that whenever P will hold, then Q has to hold, because P over here is a sufficient condition for happening of Q. If P is holding, if P is happening, if P is existing, if P is occurring, then it is sufficient for Q to occur. It is a sufficient condition for occurrence or happening or existence of Q. So if you say, if P occurs, this implies triangle ABC is equilateral. Suppose P is occurring, that means you have a triangle ABC which is equilateral, that means all the three sides of that triangle are equal. Then clearly if three sides of the triangle are equal, then any two sides, of course you can fix any two sides which are obviously equal, right? If you have all the three sides equal, clearly any two sides are always equal. So triangle which is equilateral always can be said as isosceles, right? But triangle ABC is isosceles is statement Q. So if P occurs, that means P is holding, that means if P is true, that means triangle ABC is actually equilateral, but if it is equilateral, it means it is isosceles, and that means Q occurs. So whenever P occurs, Q is occurring. Whenever a triangle is equilateral, then clearly it is isosceles. So I say that P implies Q is valid. Similarly, here I am saying if A and B are integers, then AB is a rational number. Whatever is written after if is, say, statement R, and AB is a rational number, say this is statement S. So if R, then S. What are the component statements? If R, then S. R and S are the component statements for the second particular compound statement. R is A and B are integers, and S is that A into B is a rational number. Is it clear? A into B is a rational number. How can you say that if R then S is a valid or an invalid statement? Again, whenever R will occur, then S has to occur. If that happens, then R implies S is a correct or true or valid statement. So let R hold, that means let R occur. This implies let A and B be integers. If A and B are integers, then when you multiply two integers, you get an integer. This implies AB is an integer. And any integer clearly is obviously a rational number, because you can write an integer as integer upon 1, and that is going to mean it is a rational number. So this implies A into B is rational. But A into B is rational means that S holds. So let R hold. Whenever R is holding, S is holding. Therefore, what happens? R implies S is valid. Clear? Because whenever R is holding, S is also holding. Moving on to the next one, what is it that we have? Let's see. Check whether or used in the following compound statement is exclusive or inclusive. Write the component statement of this compound statement and use them to check whether the compound statement is true or not. Justify your answer. So the statement given to you is, you are wet when it rains or when you are in a river. You are wet when it rains or you are in a river. Try to understand. You are wet when it rains or you are in a river. So basically this particular statement is using the connective or. The statement is P or Q. Try to get the statement. You are wet when it rains. It's a true statement, right? You obviously get wet when it rains. It holds the truth value of being true. You get wet when you are in a river. This also is a simple statement in here and it is a true statement. But suppose you are in a river and it is raining, even then of course you can get wet, right? Even then of course you can get wet. That means P is occurring or Q is occurring or both P and Q are occurring is making this statement valid. That means or is in here including the very case P and Q both. It's not exactly one of P and Q, right? It's not like P is true or Q is true but both are not true or both are not occurring simultaneously. But here even when both occur simultaneously you are bound to get wet. Therefore here or is inclusive because it can happen that you get wet when it's raining and you are in a river. That means both the situations are happening. That can happen, right? And therefore or is inclusive. Your or is inclusive. Then it is saying write the component statement. This is your component statement. Component statements are P and Q. P is you are wet when it rains and Q is you are wet when you are in a river. This is your P and Q. So your component statements are what? Let's write the component statements associated to this compound statement. You are wet when it rains. And next one is you are wet when you are in a river. Of course, this is holding truth value of being a true statement. This is holding truth value of being a true statement. P or Q. We have to check the validity of P or Q. P or Q is true when either P is true, Q is not true, or Q is true, P is not true, or both are true. P or Q statement is false only and only when both P and Q are false. Right now you can see P and Q both are true and this is the situation when I can say P or Q is true. Therefore, P or Q, which is my statement T, is valid, or you can say true, as both P and Q are true. And P or Q statement is false only and only when both P and Q are false. If P is true, Q is not true, or Q is true, P is not true, or both are true, then P or Q is true. Moving to the next, we have write the negation of the following statements. This is pretty easy. Let's discuss this. Okay. The first statement is, for every real number x, x square is greater than x. What is its negation? What is the negation of for every? There exists a real number x such that x square is not greater than x, that means it is less than equal to x. Either you can say it's not greater than x, that means like this, not greater than x or less than equal to x. This is the negation. Q is there exists a rational number x such that x square is 2. Its negation is what? For every rational number x, x square is not equal to 2. You pick up any rational number x, x square is not equal to 2 is the negation of that there exists a rational number whose square is equal to 2. All birds have wings. All birds have wings. There exists at least one bird which has no wings. Which has no wings. Fine, this is the negation. And then you have all students study mathematics at the elementary level there exists a student which does not study, mathematics at elementary level. This is the negation of the given statement S. Is it clear? This is how you write the negation. It's pretty easy. It's just for every is the quantifier whose negation is going to be. The statement involving for every is going to have its negation involving there exist. The statement involving there exist is going to have its negation involving the quantifier for every. Next we have, for the given statement, identify the necessary and sufficient conditions. So, statement is given by the name T. If you drive over 80 kilometers per hour, then you will get a fine. So, here statement T is actually if P then Q, where what is my P? It's an if then implication. You drive over 80 kilometers per hour. You drive over 80 kilometers per hour is P and you will get a fine is Q. So, P is you drive over 80 kilometers per hour. Okay, and then Q is you get a fine. Write the necessary and sufficient condition. You know that in the statement if P then Q, Q happens to be the necessary condition and P happens to be the sufficient condition. Why? I am saying if you drive here, if you drive over 80 kilometers, then this is sufficient for you to get a fine, right? Isn't it? The moment you drive over 80 kilometers, this is sufficient condition for you to be imposed a fine. Therefore, P is sufficient condition. P is sufficient condition for Q. And why am I saying Q is a necessary condition for P? And if you drive over 80 kilometers per hour, then necessarily you get a fine. So, getting a fine is a necessary condition for happening of the very situation of driving over 80 kilometers per hour. Therefore, Q is a necessary condition for P. Is it understood? That's how you write the necessary and sufficient condition. Next, let's see what we have. We have, using the word necessary and sufficient, rewrite this statement. The integer n is odd if and only if n square is odd, and check whether this statement is valid or invalid. The integer n is odd if and only if n square is odd means what? You know that P if and only if Q means that P implies Q and Q implies P. This is what is the meaning of P if and only if Q. That's how we define it. Write the necessary and sufficient condition. Here you can see P is sufficient for Q, here Q is sufficient for P. Here Q is necessary for P, here P is necessary for Q. That is what we conclude from the if then implication. This is if P then Q, if Q then P. So how do you actually write the integer n is odd if and only if n square is odd using the phrase necessary and sufficient? I write the necessary and sufficient condition. The necessary and sufficient condition for n to be odd is that n square must be odd, isn't it? I have just written that the necessary and sufficient condition for P to hold is that Q holds. Okay, for P to hold is that Q hold. Holding of P is necessary and sufficient for holding of Q, and holding of Q is necessary and sufficient for holding of P. So I have written the necessary and sufficient condition for n to be odd is that n square must be odd. I am taking n to be odd as P and n square to be odd as Q. These are my component statements for this compound statement P if and only if Q. Check whether the statement is valid or not. Well, I know that P if and only if Q is valid provided P implies Q is valid and along with it Q implies P is valid. So basically, to conclude about validity or invalidity of P if and only if Q, I will have to check the validity of P implies Q and Q implies P. Even if one turns out to be invalid among these two, I declare P if and only if Q is invalid. So let's talk about the validity of P implies Q and talk about the validity of Q implies P. Validity of P implies Q. How do you prove P implies Q is valid? You assume P is holding and with that assumption show that Q holds. So let P hold. P we have taken as n is odd. That is, n is an odd integer. If n is odd, this implies n is of the form 2k plus 1 where k is some integer. Any odd number can be written as 2 into k plus 1 where k is some integer, and any even number can be written as 2 into k where k is some integer, some multiple of 2. So n square will be what? 2k plus 1 whole square, which is 4k square plus 1 plus 4k. So I can write 2 common, 2k square plus 2k plus 1. Of course, this is some integer m. So I have written this as 2m plus 1 where m is an integer. This implies n square is odd, but n square is odd is statement Q. So therefore Q holds. So when I have assumed P is holding, I have got the conclusion that Q is holding. That means if P then Q is valid. Now just if Q then P also turns out to be valid, I will just write that P if and only if Q is valid. So next we have validity of Q implies P. I have to show if n square is odd, then n is odd is a true statement. So either show Q implies P is true or show its contrapositive is true is the same thing. Not P implies not Q. If not P implies not Q is valid, clearly Q implies P is valid. If not Q implies not P is invalid, Q implies P is invalid. It's the exact same thing said in a different fashion. That is, validity of if then implication, you prove that, or you prove validity of its contrapositive, it's exactly the same. So I have to show not P implies not Q. That means, what is not P? Not P is if n is not odd, then n square must be not odd. If n is not odd, then n square is not odd. This is valid. I have to show this. So if n is not odd, then n square is not odd, I have to show. So let us assume n is not odd. I am saying let n is not odd. This implies n is an even number. N is an even integer. If n is even, that means it can be written as a multiple of 2 for some integer k, which implies n square is 4k square. I can write this as twice of 2k square. 2k square is again some integer m, because k is an integer, so 2k square is an integer. So this implies n square I have written as 2m, where m is an integer. If n square is written as a multiple of 2, this implies n square is even. If n square is even, this implies n square is not odd. So I assumed n is not odd, and I proved that in that situation n square is not odd, and therefore not p implies not q is valid, and by the contrapositive approach I have proven that this implies, or therefore q implies p is valid. And if you mark this as 1 and mark this as 2, we have got p implies q is valid and q implies p is valid. So by 1 and 2, p if and only if q is valid. Is it clear? That's how you deal with questions from mathematical reasoning. Thank you.